Alright, so this is section 2 of chapter 3, and it's the mean value theorem. So this is the theorem for, this is how it's stated. If f is a continuous function, or continuous in the closed interval and differentiable in the open, then there exists some c that f of c is equal to f of b minus f of a over b minus a. All it is saying is that no matter what, between a and b, points a and b, there, like the slope between a and b, the straight exact slope, whatever function is drawn, at some point on that function, like this curved one, there will be a tangent line slope similar to the slope between that equals this equation. So like on this drawn line, even though it goes all the way up, it has to come back down at some point, and at some point it's going to have the same, at the very top, at the same slope as the line between the 2 points. So 31 is asking us to draw the tangent line on the graph that equal the tangent line between the 2 points. So there's 2. First draw the line, then you have the 2 points. There's one at the relative minimum near A, and one at the top, the maximum. And it's just teaching us to see it with our eye and be able to identify what's going on, what we want to see. 33. It's asking us to explain why this is not, the theorem doesn't apply. Remember, the theorem only works when it has differentiable and continuity. This is not continuous on its interval because of this hole and it jumps. That's not continuity, and that's a big reminder of what continuity is for this chapter, that it has to be, we'll also see in a second, cusps are not for continuity either, because it's not a continuous graph. It can't be differentiable. This point is not differentiable, so it's not continuous, or vice versa. And here is 34 asking the same question again: why does the theorem not apply? And because, well, it applies it everywhere, minus my bad drawing, but everywhere but right there, at that cusp. And at that cusp, it is not, it's not differentiable, because it's not continuous, it's abrupt, it's just it's easiest to just see it why it's not continuous, and it's because that there's so many different, like, it's a point rather than just a angle. It's an angle, it's a point. I don't know how you want to define it, but it's just because you can take so many different like you can take that derivative at here, or you can take it right here. You see, and that's not the idea of differentiable, that there's so many different ways you can take it, that there's like lots of little tangent lines. That's just like a point, so it's not differentiable, it's not continuous. Okay, 39. Now we're going to be doing the mean value theorem by eyesight. So, or not by eyesight, by math. 39 is asking us to pretty much first make sure whether it can be, the theorem can be applied, and then find the values of c that on the graph that equal the slope between the 2 points. So first, just by our simple knowledge, x squared, it's a parabola, it's continuous, it just makes a simple little arc. It's you can graph it first if you like, but it's kind of, if you've been in calculus long enough, that you can kind of just figure that out in your head. So we're just going to do f of b minus a, and we get 1 over 4, or 1 minus 4 over 3, and then negative 3 over 3, which is negative 1. So the slope between the 2 points is negative 1. So how do we figure that out? First we have to find the derivative. Then we want to set the derivative to that slope and see what values we get. And we get, so at x equals negative 1/2, that has the same slope as the tangent line between the 2 points. And then 42, again, we check within your brain to make sure that it's differentiable and continuous. We see that there would be a vertical asymptote at x equals 0, but it's not asking between that interval, so we're all good. So we just got to find the tangent line between the 2 points, or the slope, and then we have we find the derivative, we set it equal -1, and we get that at x equals 1, it is the same slope as the mean value in theorem states. So that's 42, and I hope that helped.